So for today, what we're going to do is to solve some exponential and logarithmic equations. So at the beginning, we will recall integer exponents and fractional exponents, and then we will extend the concepts to real exponents, meaning we will also include the irrational numbers as exponents. And then we will recall some of the properties of exponents. And then we will define what we call logarithm. And our main goal is to solve exponential equations and logarithmic equations. So let us start with this recall. We let a to be a positive real number and n to be any natural number. So meaning n equals 1, 2, 3, etc. Or simply n is a positive integer. Okay? And then we defined before a to the n to be a times a times a times a. We have n factors here. So a is multiplied with itself n times. So this is a to the n. And then we defined a to the 0 to be equal to 1. So in here, we assume a is a positive real number. Okay, so this is always defined. Okay, and then we have considered negative integers by defining a raised to negative n. So again, take note, n is a positive integer, so negative n is a negative integer. So a raised to negative n, we defined it to be 1 over a to the n. So if we have a negative exponent, we put it to the other side of the bar for your fractions. Okay? And then if n is greater than 1 and m is any integer, so here n is still a positive integer, but this time greater than 1, meaning starting from 2. So 2, 3, 4, etc. Okay? And then we take m to be any integers. Okay? We defined a raised to m over n to be the nth root of a raised to the power m, or we can also write it as the nth root of a to the power m. Okay, so either we put the m, the power m, outside the radical, or we do the exponentiation first, like a to the m, before getting the nth root. Okay, and again, this is defined. Okay, this is well defined because we are assuming a to be a positive real number. So we are not considering negative negative values for a. Okay, so these three guys here considers or consider positive and negative and also zero. Okay, positive and negative integers and also zero. This bullet here now considers fractions as exponents. Okay? So the question is, what about a to the x for any real number x? Okay? In particular, what if x is an irrational number? Okay? What if x is an irrational number? Because in here we have the integers and then we have the rational. So the remaining set from the set of real numbers that is not being considered is the set of irrational numbers. So what now if we have x to be irrational? So let us consider this number here, 3 raised to pi. So I hope you still remember pi. Okay. So pi, the number pi, is approximated by 3. Okay. It is also approximated by 3.1. It is approximated also by 3.14. This is the one that we always use. Okay, 3.14. But we can extend this. Okay, pi is also approximated by 3.1415, and so on and so forth. If we write pi, okay, pi is approximately equal to 3.14159259265, etc. Okay, so this is longer, at least longer, or have or has more decimal places compared to this. But you can have infinitely many decimal places for pi. Okay? So we have an approximation for pi. Okay? What we're going to do is to have also an approximation for 3 to the pi. For example, let us start with 3 to the 3 because pi is approximated by 3. Then we have 3 to the 3 here. Okay? This 3 to the pi is approximated by 3 to the 3, and that's equal to 27. Okay? Since pi is approximated by 3.1 also, a better approximation than 3, okay? Then 3 to the pi can be approximated by 3 raised to 3.1. And 3.1, this is just a rational number, meaning it can be written as a fraction, which is 31 over 10. So 3 raised to 31 over 10, this is the 10th root of 3 raised to 31. So if we use our calculator, compute for this, we will get 30.1353. Now, your pi is also approximated by 3.14. So 3 to the pi can also be approximated by 3 raised to 3.14. And 3.14, it's also a rational number. As a fraction, it is written as 314 divided by 100. So if we calculate this, this is 31.4891. Okay? Then we continue the process. Here we have 3.141 for an approximation of pi. It's not written in here because I skipped it here. Okay? But again, 3.141, it's just a rational number, and its fraction form, it's 3,141 over 1,000. So if we calculate this, we will get 31.5237. And also, we have 3 raised to 3.1415. This approximates 3 raised to pi. And again, this number here, it's a rational number. And if we calculate this, this is equal to 31.5411. And we can continue. Okay? We can continue. We will get a better approximate for pi. Okay? We can extend these numbers here if you know. Okay? But that number is just an approximation of 3 to the pi. And I have calculated here 3 to the pi, it's actually equal to 31.5442807001975, blah, blah, blah. So this decimal here won't stop, okay? Or possibly it will stop, but we don't know, okay? But this can continue. And those digits there, you can obtain it by getting a better approximate for the value of pi, okay? But as you can see, started from 27 and then 30.1353, etc. until we got here 31.5411. Okay, so notice from this line, we now have at 31. Okay, and then from this line, we now have at 31.5. You see that 31.5, but this is 5.2. But from this line, we now have 31.54. And then the next digit here is 1. Here we have 5, 4, and then 4. So maybe if we have the next digit for the pi, it will give us a closer number to this. In fact, it will give us the closer number. Okay? So that's how we do it. Okay? For exponents which has irrational power. Okay? Or power which has irrational exponents. Okay? So it's not as easy as the integer exponent or the fractional exponent, because there's a possibility that the resulting number, okay, that the resulting number is an irrational number also. Okay, but this is how we do it. This is how we do it, possibly. Okay, which means it's the same as the integer exponents. It's the same as the fractional exponents, okay? So that we will have the same properties. So we are only extending the properties of exponents to the real exponents now. So from integer, then to fractional, this time we have the real exponents. So we let a, b, x, y be real numbers with a and b positive numbers. Okay? So the value of a to the x, okay, this is a unique real number. There's only one number for a to the x. Okay? Of course, your a is fixed, your x is fixed. So a to the x, it's a fixed number. Okay? Now, if we recall all those properties of exponents, okay, we just put it here. You have same base, okay? You have a to the x times a to the y, so same base. What you can do is just to add the exponents. So this is the same as a to the x plus y. So same property. Also, if you have here a to the x divided by a to the y, this is a raised to x minus y. And then if you have a to the x to the y, this is just the same as a to the xy. Okay? And let me just extend this. This is the same as a to the yx, and this is also the same as a to the y to the x. Okay? So meaning you can interchange the two. Okay? You can interchange x and y in here. It will give you the same number. Okay? And then you have AB. You have the product AB. You raise it to power x. It's the same as a to the x times b to the x. And then, of course, you have the product here. You also have the quotient. So a over b to the power x, it's equal to a to the x over b to the x. Okay? Now, I will add some more properties. If a is greater than 1, so take note of that. If a is greater than 1, and you have x less than y, then a to the x will also be less than a to the y. Okay? So take note of this. If a is greater than 1, and if x is less than y, a to the x will also be less than a to the y. On the other hand, if a is less than 1 but greater than 0, so if a is between 0 and 1, exclusive of 0 and 1, and also your x is less than y, so same condition as in the number 3, this time the inequality will change. A to the x will be greater than a to the y. Okay? So again, if a is greater than 1 and x is less than y, a to the x will also be less than a to the y. On the other hand, if a is greater than 0 but less than 1 and x is less than y, we will get a to the x greater than a to the y. Okay? Question so far? Let's look at this example. So we let x equals 2, and then your y equals pi. So it's roughly 3.14, and 2 is less than pi. Correct? So x is less than y. So this guy here is satisfied. X is less than y. Okay? Now, let's take a to be 3. 3 is greater than 1. Okay? Your 3 is greater than 1. So we are looking at bullet number 3 here. So we have a greater than 1 and we have x less than y. And then we solve for a to the x. That's 3 squared. X is equal to 2. 3 squared, that's 9. And then a to the y, that's 3 to the pi. And I showed you earlier, 3 to the pi, it's 31.54428, blah, blah. And you see, a to the x, which is 9, is less than a to the y, which is this guy here. So a to the x is less than a to the y. So that illustrates number 3 here. And then, what if we have a equals 1/3? So 1/3 it's less than 1, but greater than 0. Okay, so we are now trying to illustrate number 4. And we will still use x and y here. So we still have x less than y. But if we compute a to the x, or 1/3 squared, that's 1/9. And in decimal, it's 0.1111, etc. While a to the y, it's 1/3 raised to pi. If you calculate this, you will get 0.0317, blah, blah. And of course, 0.03, it's less than 0.11. Think of this as 0.11, while this guy here, it's 0.03. Okay? So we have the conclusion, a to the x greater than a to the y. Okay? So we have verified at least for this, using this example, we have verified number 4 and number 3 theorem here. But this is true in general case. As long as your a is greater than 1 and x is less than y, a to the x will also be less than a to the y. As long as your a is between 0 and 1, not including 0 and 1, and your x is still less than y, the value of a to the x will be greater than a to the y. Okay? Question? Now, of course, you know this pi. It's roughly 3.14. I will introduce another number. Okay? Let us consider 1 plus 1 over x raised to x. Okay? What we're going to do is to replace x with some numbers and compute the value of this expression here. 1 plus 1 over x raised to x. Okay? More precisely, we will replace x with values that are increasing. Okay? So for example, first, suppose we let x equals 1. So if x is equal to 1, you have 1 plus 1 over 1, that's just 2. Then raised to 1, you have 2. Okay? Now, if x is equal to 10, okay, if x is equal to 10, we will have 1 plus 1 over 10 raised to the power 10. Okay? So try to calculate it. This is what you will get. 2.59374244601. So from 1, we increase it to 10. Let's increase it further to 100. Okay? So if x is equal to 100, you will have 1 plus 1 over 100 raised to 100. What you will get is 2.70481. And there are more digits here. And then you continue the process. Say we have 1,000. X equals 1,000. You will get 2.7169239, etc. And then increase X further. Say this guy here, it's 1 million. So if X is equal to 1 million, 1 plus 1 over 1 million raised to 1 million, you will get this number, 2.71828046939, etc. Okay? So observe, as we increase this value of X, the value of 1 plus 1 over X raised to X goes something like this. You have the 2 and then 2.59. So the difference between this guy here and this guy here is 0.59. And then from this guy here up to this guy here, you have 2.5937 blah blah. This guy here, it's 2.7048. So look at the difference. The difference between this guy and this guy here, it's roughly 0.11 or 0.10, 0.10 blah blah. But from this guy to this guy, so from 100 to 1,000, from this guy to this guy, the difference is just 0.01 something. Okay? And then from this guy to this guy, the difference is now 0.001 or 0.002, etc. But the point is, the difference between this and the next item for your table here, it becomes smaller and smaller. Okay? And in fact, for sufficiently large X, okay, say you have X equals 1 billion, 1 trillion, or 1 Google, etc. If you let your X go to some very, 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 very large number, you will get something like this. And in fact, it will be very close to this number E. Okay? And in fact, not really, yeah, that's very close only because you have a very fixed large number. Okay? So in fact, this number E is defined to be this guy here, this expression here. So this expression here, particularly this guy here, you will see this in calculus. You will see this in calculus 1. But I am introducing it to you. This is called the limit, or this is read as the limit of 1 plus 1 over x raised to x as x goes to plus infinity. Okay? So this guy here only means that you let your x go to very, 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 very large number. Okay? You let your x go to very, 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 very large number. And you observe what will happen to this guy here. Okay? So in here, you let your x to go to very, 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 very large number. You observe what will happen to this guy here. Okay? And it turns out, if you let your x go to some very, 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 very large number, you will get a fixed number. Okay? It will go to some real number. And the real number was called E. Okay? This E is approximately 2.71828. That's what you see in here. 2.71828. Okay? So if you choose X to be greater than 1 million, this 71828 will be fixed already. So this will change. And then if you make it larger, this guy here may be fixed, whatever number the next number would be. But the point is, you now have a number which is denoted by this symbol E, okay? And this E is very close to 2.71828. Okay? And this E here, it's an irrational number, just like your number pi. Okay? This is an irrational number. Okay? So that one. I just have to introduce it because it is useful in our computations and even in possibly future courses. Okay? So we have that number E. And if you see some E, do not convert it. Do not convert it to the decimal representation because it will not be converted anyway to the exact value of E. So just write E. Okay? You can also see that in your calculator. There is some number there, or there is some character there, which looks like E, but that character is actually this number here. Okay? So question so far? All right. So now, what we're going to do next is to define what we call logarithms. Okay? So these logarithms is actually related to your exponents. Okay? So let a be greater than 0 with a not equal to 1. So we want a to be positive but not equal to 1. Then y is the logarithm of x with base a. So we denote it like this. Y equals log x, and then a is a subscript of log. Okay? That's how we denote this guy here. If a to the y equals x. Okay? If a to the y equals x. So this expression here, if and only if you have a to the y equals x. So notice how the name base here appears. Okay, when we talk about exponents, this guy here, it's called a base. Correct? We have the base, we have the exponent, and then we have the power. The base is the one you write in here. In logarithm, it's also called a base. Okay? So y equals logarithm of x base a. This is the same thing as a. You raise it to y, it will give you x. Okay? So you get the logarithm of x with base a. The number will be y. Okay? That's the same thing as if you raise your a to that number y, it will give you x. Okay? If this is new to you, it's okay because at this point of your course, most of the students have seen this guy here for the first time. So don't worry about that. Okay? But with the use of the examples, I hope the definition will retain to you. Okay? So let us look at the first example here. Oh, by the way, if your A, okay, if your A is equal to 10, we just write log. Okay, we just write log. We remove that subscript. Okay, meaning log x, it's equal to log x with base 10. Okay, also, if your a is equal to the number e that I introduced earlier, okay, if a is equal to e, we write this guy here. It's ln. Okay, that's ln instead of log with base e. Okay, so look at that. If a is equal to 10, we write log instead of log 10. Log base 10, I mean. If a is equal to e, we write ln instead of log base e. And for other numbers of a, we will put the subscript. Okay? So for example, here, we know 4 squared, that's equal to 16. Okay? So from exponential, we will write it as a logarithm. Okay? So if we go back to this guy here, okay? This is your x, okay? This is your a, and this guy here, it's your y. Okay? You look at this. So in terms of logarithm, y, that's your 2 here. Your x, that's the one inside the log. Okay? That's the one inside the log. And then your a here, the base a, it's your subscript for log. Okay? To avoid confusion, you can put the x inside the parenthesis. Okay? Meaning you are getting the logarithm of x. So in here, you are getting the logarithm of 16. Okay? So this example here helps us convert exponential expression into logarithms. So 4 squared equals 16. That's the same as logarithm of 16 base 4 equals 2. Okay? Next example. Here, we have 3 raised to negative 3. But we know if we have a negative exponent, we can bring it to the denominator. Correct? So this guy here, we can write as 1 over 3 to the power 3. And this guy here, it's the same as this. Correct? So 3 raised to negative 3, that's the same as 1/3 raised to the power 3. And 1/3 raised to the power 3, that's 1 over 27. Okay? Or even coming from here, you know that 3 to the 3, that's 27. So you have 1/3 raised to 3 to the 3. 1 over 3 raised to 3, that's 1 over 27. But what's the point in here? We convert it to logarithmic expression. So again, this guy here, it's your base A. This guy here, it's your x. And this guy here, it's your y. So converting, so we do the comparison in this guy, in this expression or this equation. So if we convert it to logarithm, this is what we will get. Logarithm of x, which is 1 over 27, with base 3, Look at that. A with base 3. That is equal to the y. But y is negative 3 here. So logarithm of 1 over 27 with base 3, that's equal to negative 3. Okay? Next example here, we have 16 raised to 5 over 4. If you calculate this, this is equal to 32. Okay? So 16 raised to 5 over 4, that's equal to 32. So as in before, we have here your y, and then this is your base a, and this is your x. So converting to logarithm, the logarithm of 32 with base 16, so logarithm of 32 with base 16, that's equal to 5 over 4, the value of y there. Okay? So again, y equals log x with base a. This is equivalent to a raised to power y. This is equal to x. Okay? Question. Now, let us look at some properties of these logarithms. So let a, b, and c, r be any real numbers where a, b, and c greater than 0 and your a is not equal to 1. Okay? So a, b, c are real numbers. Your a, b, c are all positive, but your a cannot be equal to 1. Then, the logarithm of the product bc with base a, this is equal to logarithm of b with base a plus logarithm of c with base a. So meaning, if you have a product inside the logarithm, you can separate them into two logarithms. Okay? So logarithm of the product, it's the sum of logarithms. If we have the product, we also have a quotient. The logarithm of b over c with base a, this is equal to logarithm of b with base a minus logarithm of c with base a. So for product, you have the sum here. For quotient, you have the minus. But what I want to emphasize is, if you have several numbers in the quotient or in the denominator, when you separate them, they will have minus. Okay? As a coefficient of the log. If you have several numbers in the numerator like this, the coefficient of the log is plus. Okay? So these two guys here converts several logarithms or sum or difference of logarithms into a single logarithm. So you have two or more logarithmic expressions, all have the same base. So base A, there are more with base A. You can combine them into a single logarithm with base A. So that's the point of 1 and 2. Okay? Now, what if your C is the same as B? So you will have B times B, which is B squared. For b squared, we will have what? Log b plus log b. So you will have 2 log b. We extend that. What if your b has an exponent r? Then this r here can go down as a coefficient of logarithm. So take note of this. The r is an exponent of b. So log of b to the r with base a, this is equal to r logarithm of b with base a. So the exponent, it just went down as a coefficient of the logarithm. Okay? To avoid confusion, that r now is being multiplied to the number logarithm of b with base a. Okay? Question? Another property here, your a raised to power r, you can write this as a raised to r ln of a. So your your a raised to r, it's equal to e raised to r ln of a. Okay? So a to the r is equal to e, the number e that I introduced earlier, with exponent r times ln of a. And again, ln here, it's a logarithm with base e. Okay? ln here, it's a logarithm with base e. Another property here, if logarithm of b with base a equals logarithm of c with base a, then b must be equal to c. So equality of logarithms with the same base, the arguments b and c here must be the same also. And in here, logarithm of a with base a, so you are taking the logarithm of the number a, the same as the base of the logarithm, that's equal to 1. Whatever your a is, any positive number with a not equal to 1. So if this argument here is the same as the base, then the logarithm is just 1. And finally, last property in this part, the logarithm of 1 with any base, okay, whatever your base is, the logarithm of 1, it's always equal to 0. Okay? So the logarithm of 1 with any base a, that's always equal to 0. Logarithm of a with base a, that's equal to 1. Okay? So these properties are the properties that these are the only properties that we will use in this course. If there are any, they will be presented later. Okay? Now, I want to emphasize the following. You may have logarithm with base a of b plus c. Okay? But we don't have any property for this. It's just as is. Okay? So to be more precise, what I want to say is that the logarithm of b plus c with base a, this is not the same as the logarithm of b with base a plus logarithm of c with base a. This guy here, the right-hand side, it's a product, b times c. Okay? But for this guy, we don't have anything. So this is a common mistake. Do not do this. Okay? So do not do this. I mean, you don't distribute your logarithm to each of B or C. Okay? Also, this logarithm of B with base A to the power R, this is not the same as the logarithm with base A of B to the R. So in this part, the exponent of R is on B. It's this guy here. On the other hand, in here, the exponent R, it's on the logarithm of B with base A. So on the left-hand side, you compute first the logarithm of B with base A before raising it to exponent R. On the right-hand side, you compute first B to the R before getting the logarithm. Okay? Let us now consider some examples. Express the following as a sum or difference of logarithms. Okay? So look at this. You have the log with base 3 of x squared cube root of x plus 2. When you see radicals, convert it to exponents. Okay? So for instance, in here, you have log with base 3 of x squared cube root of x plus 3. So you convert this, sorry, it's x plus 2. But anyway, you convert this radical into exponent. So let us rewrite it as the log with base 3 of x squared times x plus 2 raised to 1 over 3. Okay? Now, you have a product, x squared times x plus 2 raised to 1/3. So we are going to use the property log BC with base A. Okay? This is equal to log of B with base A plus log of C with base A. So from product, we change it to sum. Okay? So we do that here. We get log base 3 of x squared plus log base 3 of x plus 2 raised to 1/3. Now, x has exponent 2, x plus 2 has exponent 1/3. So we use now the property r log b with base a. This is equal to log with base a of b raised to r. So the exponent of b, it will become a coefficient of log, which means in here we will get 2 log with base 3 of x. So you bring this exponent 2 here as a coefficient of log. In here, you bring the 1/3 as a coefficient of log. So plus 1/3 log with base 3 of x plus 2. And this is the final expression. Okay? So this guy here, it's a final expression. Take note, you have x plus 2 here and there's nothing to do there. Okay? Question? Let's go to our next example. So we have log of x over x squared plus 5 raised to power 2. And take note, you don't see any number here as a base, so the base here is automatically 10. Okay? And then you have a quotient. So if you have a quotient, this is the property that we're going to use. Log of b over c with base a. Okay, let me just move this a bit. So log of b over c with base a, this is equal to log of b with base a minus log of c with base a. So for the denominators, we put minus. For the numerators, we put plus. Okay? Therefore, for the original problem, we have log of x over x squared plus 5 quantity squared. This is now written as log x minus log of x squared plus 5 raised to power 2. Okay? And as in before, this exponent here, it's the exponent of x squared plus 5. So we can bring these two as a coefficient of the logarithm. And therefore, we will have log of x minus 2 log of x squared plus 5. And this is the final expression. Okay? So the previous example and this example illustrates how to convert logarithm of products or quotients into sum of logarithms. Okay? So they illustrate conversion from products of difference to sum of logs. Sorry, products or quotients to sum of logs. Sum or difference of logs. Now, in this next example, we reverse the process. We have sum or difference of log. We write it as a single logarithm. Okay? So again, this is ln, so it's the log with base e. Okay? You see here, it's just plus. You also have plus in here, and then you have the minus. Okay? So for all of those in the plus, okay, for all of those in the plus, the arguments will be in the numerator. For those with the minus, we just have one here. Okay, this guy here will be in the denominator. Okay, which means here we have ln of 9 times x. Okay, and then here we have minus, so this guy here will be on the denominator. X squared plus 3. And that's it. Okay? So from sum or difference of logarithms, we now we now able to write them as a single logarithm. Question? Next here, again, we convert this to a single logarithm, but this time you have coefficients other than 1 or -1. So we use the property that this coefficient here becomes the exponent of the argument. This coefficient 1 half here becomes the exponent of the argument. Okay? So what I'm saying is, this expression now, first can be written as log base 5 of 3 to the power 2, and then minus log base 5 of x minus 5 to the power 1/2. And then we now have positive here or negative here. So this will go to the numerator. This will go to the denominator for the single log. So this guy here becomes log base 5 of 3 squared. So let me just write it as 3 squared. Okay? Divided by x minus 5 raised to 1/2. And then you can convert 3 squared to 9. Correct? So you can have your final answer written this way, or you can have log base 5, and then you have your 9 divided by x minus 5 raised to 1/2. So either this guy here or this guy here should be fine. Okay? So the last slide and this slide here, let us convert sum or difference of logarithms into single logarithm. And then in the previous examples, we had conversion from single logarithms to sum or difference of logarithms. Okay? Now, for the next example here, we want to convert base. So we want to express logarithm of x with base 3 as an expression involving logarithms with base 5. Okay? So this means, can we write log of x with base 3 into something with log 5? Okay? That's possible. Okay? How do we do that? So first, we will start with setting the number y to be the log x base 3. Okay? But this guy here, according to our definition, let me write the definition. You have your y equals log x base a if and only if a to the y, this is equal to x. So we will use this. Okay? This means that this expression here It's simply 3 to the y equals x. Okay? Now, we want logarithms with base 5. And we don't see any logarithm in this part here. So what we're going to do, so 3 to the y, it's just a number, and it's written as x. So if I get the logarithm of 3 to the y, I should also get the logarithm of x to retain the equality. Correct? Particularly, we will use logarithm base 5. We will apply that on the left, and therefore we apply that also on the right. So you have the logarithm base 5 of 3 to the y. This is now equal to logarithm of x, and again, this is base 5. Correct? And now, you have here 3 to the y. Y is an exponent of 3, so this y can go down. This guy here becomes y logarithm with base 5 of 3. And this is equal to logarithm of x with base 5. Okay? But logarithm of 3 with base 5, this is just a number. And this is not equal to 0. Okay? This is not equal to 0. Meaning we can divide everything by log 3 base 5. So let me write that. So y log 3 base 5, we divide this by log 3 base 5. And therefore, we should do the same on the right-hand side. Log x with base 5 divided by log 3 with base 5. But this guy here will cancel this, which means that y is equal to log x base 5 divided by log 3 base 5. So, but y here? It's your log x base 3. Okay? So, we have converted log x base 3 to something with base 5. Okay? So, this guy here, this is equal to log base 3 or log x of base 3. So, they are the same. Okay? And this guy here, this method here, okay, only shows the following: change of base logarithm of logarithm. Meaning, if we have one base, we can convert it to another base. So let a and b be positive, with a not equal to 1 and b not equal to 1. And let x be any positive number. Then, the log of x with base a, that's equal to log of x with base b, divided by log of a with base b. Okay? So you replace the base a to the new base b, but you divide it. Okay? You divide this by the logarithm of the original base with base new base b. Did you get that? So log of x with base a, that's equal to log of x with base b divided by log of a with base b. Which means, if you can remember this formula, you can change log of x with base 3 with any expression involving other with involving other bases. So you can convert log x base 3 to an expression involving logarithms with other bases. So you can have log of x base 3, that's our original. You can write this as log of x base 5 over log x base 5. Oops, log 3, sorry, log 3 base 5. And this is the same as log x base, say, 20 divided by log x or log 3 base 20. And this is the same as log x base 100 over log 3 base 100, etc. Okay? And you will see this in the module, this formula here. Okay? So I just want to clarify this. This is, since this is 100, this is base 100 here. Okay? Looks like 110. So just to clarify. Now, our goal for the lecture is to compute or to solve exponential equations and logarithmic equations. Okay? So these are some of the properties that we will use. If you have a to the m equals a to the n, so you have the same base, the exponents must be the same. So a to the m equals a to the n. This is equivalent to saying, or so this one, if and only if m equals n. So a to the m equals a to the n if and only if m equals n. Here, definition of logarithm, a to the y equals x if and only if y equals log of x with base a. So definition of logarithm that I wrote earlier. And then in here, if you have log m with base a equals log n with base a, okay, then m and n must be equal. Of course, if m equals n, you take the logarithm of left-hand side, that is equal to the logarithm of the right-hand side. So we still have if and only if in here. So these properties or this definition, particularly number 2, and these properties 1 and 3, plus the other properties that I introduced earlier, okay, they will be useful in solving equations involving exponentials and logarithms. So for the next slides here, these are all examples. Okay? So solve the following equation. Log of x plus 2 with base 2 equals 3. So if you have this kind of equation or this type of equation, you just have one log on the left-hand side and just a constant on the right-hand side or a single expression on the right-hand side. Convert this to exponential. Okay? So you have log base 2 of x plus 2. This is equal to 3. Okay? This will give us x plus 2 equals 2 to the power 3. Okay? So the base of log is 2. The base of exponent is also 2. The right-hand side become becomes, this right-hand side here becomes an exponent. Okay? But 2 to the 3, that's 2 times 2 times 2, that's equal to 8. And therefore, you have x equals 8 minus 2, or that x is equal to 6. So this is our answer. Now, in here, be careful when you have obtained a value for your variable. You have to make sure that when you substitute your candidate solution to the original equation must be well defined. Okay? Meaning, suppose I substitute x, okay, substitute x equals 6, you will get here 6 plus 2. That's equal to 8. And inside the logarithm, it must be positive. So 6 plus 2, that's positive 8. So this is well defined. Okay? And then you compute if needed. Okay? If needed, you compute, you verify the validity. And how do we do the checking on this part? Checking. Okay? When x equals 6, so x equals 6, you have log base 2 of 6 plus 2. But 6 plus 2, that's just 8. Log base 2 of 8. But what is 8? 8, you can write it as 2 to the power 3, just like this. So this guy here, it's log base 2, 2 to the power 3. And then you use the property. 3 can go down. Or you use the fact that you have the base 2 here and then you have an argument 2 here. It looks like they will cancel each other. Okay? But let's use the property that I listed earlier. So these 3 here can go down. You have 3 log 2 base 2. And this guy here, this is equal to 1. So you have 3 times 1, and that's your 3 on the right-hand side. So x equals 6 is a solution. Okay? So what are not solutions? For example, you have obtained some number for x. Okay? And then when you substitute it, you get negative number. Okay? You have logarithm of some negative number. That will be undefined. We only consider logarithms of positive numbers. So if you have logarithm of a negative number, then definitely that one cannot be defined, and therefore the associated variable, the associated value of the variable is not a solution. Okay? Next problem here, solve the equation. 2 log of x plus 4 base 3 minus log 9 base 3 equals 2. Now you have two logarithms, logarithmic expression, this guy here and this guy here. The other side, it's just constant, so that's totally fine. One way to do this is if they have the same base, like this 3 and this one is 3, you combine them into a single logarithm. Okay? That's one way. Another way, if you look at this, you have logarithm of 9 with base 3. Your 9 can be written as a power of 3. Okay? So, if you have logarithm of constants, try to simplify it first by using properties of logarithms. Okay? More precisely, for this equation here, we have 2 log base 3 of x plus 4 minus log base 3 of 9. This is equal to 2. 9, it's 3 times 3, or 3 squared. So you have log base 3 x plus 4. So 2 times logarithm of x plus 4 with base 3 minus you have logarithm with base 3 of 3 squared. That's your 9, correct? And this is equal to 2. And then this 2 here can go down and you have log 3 with base 3. So you have now 2 log of x plus 4 with base 3 minus 2 log of 3 with base 3. And that's equal to 2. And as in before, log 3 base 3, that's just 1. So in here, you have 2 log of x plus 4 with base 3. This is equal to 2 plus 2. So log 3 base 3, that's 1. And then you have now minus 2 times 1. You bring this to the other side. So it becomes plus 2. Okay? And 2 plus 2, that's equal to 4. Now we can divide by 2. So we have log x plus 4 with base 3. This is equal to 4 divided by 2. Let me write that. 4 divided by 2, and that's just equal to 2. And then we use now the definition of logarithm. We now have x plus 4. This is 3 to the power 2. And 3 to the power 2, that's again 9. And therefore, x is equal to 9 minus 4. And this is equal to 5. Okay? And this is your final answer. Of course, if you substitute x equals 5 in the original equation, you have x plus 4, that becomes 5 plus 4, that's 9. Correct? And logarithm of positive number, it's well defined. Okay? So this is your solution. You can do the checking. X equals 5. So you will have 2 log 9 base 3 minus log 9 base 3. Okay? So let's do the checking here. Checking. So x equals 5. What you have is 2 log 3, log base 3 of 5 plus 4 minus log of 9 base 3. But this becomes 2 log of 9 base 3, then minus log of 9 base 3. But you have 2 log 9 minus log 9. It's just 1 log 9 or logarithm of 9 base 3. And again, your 9, it's 3 squared. Okay? So log base 3 of 3 squared. And again, this is just 2 log 3 base 3. And this is just 2. And that's your right-hand side in here. Okay? Question? Next item here. Suppose you have this. Ln of x plus ln of x plus 3 equals ln of 4. So you have several ln's. Okay? Here you cannot simplify. Here you cannot simplify. Ln of 4, you can simplify, but let's just write it as ln of 4. If you have something like this, try to write them into a single logarithmic expression. Okay? More precisely, for the left-hand side, we write this to a single ln. Right-hand side, let's retain that to be 4. To be ln of 4, I mean. So you have plus. This means, so let's write that ln of x plus ln of x plus 3. This is equal to ln of 4. So you can combine this into a single logarithms or single logarithm. That becomes ln of x times x plus 3. Okay? And on the other side, you just have ln of 4. And remember, if you have ln of something or log of something on the left equals log of another thing, the something must equal to the another thing. So what I'm saying, here, we will now have x times x plus 3. This is equal to 4. Okay? So ln of x times x plus 3 equals ln of 4. Therefore, x times x plus 3 must be equal to 4. And then you just solve this. This is just ordinary quadratic equation. So you will have x squared plus 3x on the left-hand side. Let us put 4 to this side. So we will have minus 4. And this is equal to 0. Then you can work on this. Let's use factoring. This is x plus 4, x minus 1 equals 0. So try to check. This is the factored form of this guy here. But what does this mean? X plus 4 equals 0, or x minus 1 equals 0, which means you have x equals minus 4 or x equals 1. Now, we do the checking. So checking here, if we let x equals minus 4, so we start with this. If x equals minus 4, you will have you will have something like ln of minus 4 plus blah. But this one here is undefined. So x equals minus 4 is not a solution. Okay? X equals minus 4 is not a solution. For the other guy, you have x equals 1, ln of 1 plus ln of 1 plus 3. This is equal to ln of 1, that's 0. Remember that property. The logarithm of 1 with any base, that's equal to 0. ln is just logarithm with base e. So ln of 1, it's also equal to 0. Plus 1 plus 3 here, it's 4. So you have ln of 4. And that's precisely your right-hand side. So therefore, solution is just the x equals 1. Okay? Question. So in logarithmic equations, checking is important. Just like in your radical equations, checking is important. So you are required to do the checking. If you don't, and there are answers, there are values of the variables that are not solutions, then you will get deduction. Okay? Question? Next example. This time, we have exponential equation. So 3 to the minus x equals 27. If you have something like this, you have an exponent on the left-hand side and just a constant on the right-hand side. Look at the constant. Say in here you have 27. Try to write it, okay? Try to write it as an exponent or as a power of the same base as on the left-hand side, if possible. On the left-hand side, you have 3 raised to minus x. On the right-hand side, you have 27. But 27, you can write this as 3 raised to power 3. 3 times 3, that's 9. Times 3, that's 27. And therefore, you have 3 raised to negative x equals 3 raised to 3. This means negative x must be equal to 3, or that x is equal to negative 3. So that is your answer. You can do your checking here. Okay? You can do your checking. So I'll just leave that to you. But you see, if x equals negative 3, you have 3 raised to negative of negative 3. Negative of negative 3, that's positive 3. So 3 to the positive 3, that's precisely 27. So I'm leaving the checking part to you. Next, suppose we have two exponents on each side. Well, one exponent or one exponential expression on the left-hand side and one exponential expression on the right-hand side. Same thing as in before, check if they have the same base. On the left-hand side, we have base 2. On the right-hand side, we have base 5. So what if we have different bases? That's in that case, we will use logarithms. Okay? So if you take the logarithm of the left-hand side, you must take the logarithm of the right-hand side. So you start with the original problem, 2 raised to x plus 1. This is equal to 5 raised to 1 minus 2x. Okay? And then we use any base for the logarithm. We will take the logarithm of the left-hand side. We will also take the logarithm of the right-hand side. Let's just use base 10. So, if we have base 10, you'll just write log. So, you want to get the log of 2 raised to x plus 1. This is the same, or this should be equal to the log of 5 raised to 1 minus 2x. Correct? So what you do on the left-hand side must be done on the right-hand side. You get the log of the left-hand side. You also get the log of the right-hand side. And then from here, 2 has exponent x plus 1. We can bring it down. In here, 5 has exponent 1 minus 2x. We can also bring it down here. Which means we now have x plus 1 times log 2. On the other side, we have 1 minus 2x times log 5. Take note, log 2 is just a number, log 5 is just a number. It's a constant. So, what's next? We just distribute this log 2 to each of x and 1 here. We also distribute this log 5 to this parenthesis here. So we have log 2 times x. Okay, so log 2 times x. So x times log 2, it's the same thing. You can do that. And then you have 1 times log 2. So you just have plus log 2. On the other side, the same thing. We distribute log 5. So log 5 times 1. We have log 5. And then minus 2x times log 5. So what I'm going to do is to put the x, the variable x, on the right side, just like this guy here. So I will have 2 log 5 quantity x. Okay? So again, log 2 is just a constant. Log 5 is also a constant. This expression here, we have the variable x. This expression here, we also have the variable x. So we put on one side all the expressions with variable x. And on the other side, the constants. So I'm gonna put this to this side. Okay? So first we copy log 2 times x. Then put this on this side, it becomes plus 2 log 5 times x. This constant, log 2, I'll put it on the other side. So we will have here, let's copy log 5. And then put log 2 on the other side. So we have minus now. Okay, so minus log 2. And then in here, you see, x is a common factor. So you can factor it out. Okay, so this guy here becomes log 2 plus 2 log 5. Okay, quantity times x. And this is equal to log 5 minus log 2. Hello? And finally, you have log 2 plus 2 log 5. It's not equal to 0. Okay? This guy here, it's not equal to 0. Okay? This is also not equal to 0. Okay? Which means, if you add these two guys here, well, I'll just gonna say, the sum here, it's not equal to 0. Okay? So we can divide the whole expression by log 2 plus 2 log 5. And we will get x equals, in the numerator, you have log 5 minus log 2 divided by log 2 plus 2 log 5. 2 log 5. And this is the value for x. Okay? Now, if you would ask me, do you need to do the checking? Actually, no. You don't have to do the checking for this guy here. But if you do, the equation will be equal. The equation here, I mean, will be satisfied. Okay? Question. All right, next problem. You have 9 to the x minus 3 to the x plus 1 plus 2 equals 0. So this looks awful, okay? And it looks difficult. But let us try to simplify this. First, you have base 9 here, you have base 3 here. And 9 is just a power of 3. So we can make this guy here base 3. Okay? So you have 9 to the x minus 3 to the x plus 1 plus 2. This is equal to 0. But 9, it's 3 squared. And then you have raised to x. In here, you have 3 to the x plus 1. You can write it as 3 times 3 to the x. Correct? 3 here, it's 3 to the 1. So 3 to the 1 times 3 to the x, that's 3 to the x plus 1. 1 plus x, x plus 1. And then you have plus 2. equals 0. And then remember, you have 3 squared to the power x. You can interchange them, so that you can rewrite this as 3 to the x quantity squared minus 3 times 3 to the x plus 2 equals 0. Is it much simpler? To make it more simple, or to make it simpler, we can do this. We let y be equal to 3 to the x. So this expression here, or this equation here, can be written as y squared minus 3y plus 2 equals 0. Now it's much, much, much simpler. So this guy here is actually an equation quadratic in form, because we were able to write it as a quadratic equation. So we solve this using our methods in solving quadratic equations. Once we have the value for y, we bring back 3 to the x, and then we solve for x. Okay? But this guy here, you can factor this into y minus 2, y minus 1. So this one is equal to 0. And therefore, you have y minus 2 equals 0, or y minus 1 equals 0. Or this one will be y equals 2, or y equals 1. But what does this mean? Your y is 3 to the x. So this means 3 to the x equals 2, or 3 to the x equals 1. Correct? And what do we do with this to solve for x? For this, we can just log base 3, both sides of the equation. Okay? We have log base 3 of 3 to the x equals log base 3 of 2, or, so let me continue this part first. You know, this x will go down, and then log 3 base 3, that's just equal to 1. So this means that you have x equals log base 3 of 2. And then the or part here, you have 3 to the x equals 1. So what should be your x? What should be the power of 3, so that 3 to the power to 3 to that power will give you 1? This one should be obvious to you. It should be equal to 0, because 3 to the 0, that's 1. So these are the values for x that will solve this system. Okay? Question? For my last example, you have here 3 to the x minus 14 times 3 to the minus x equals 5. For this type of equation, you have the same base, 3 to the x, and then here you have 3 to the minus x. if you have something like this, okay, if you have something like this, you have negative exponent, try to remove that negative exponent. Okay? So what you can do is to bring it down as a denominator. That's one way. Or another way is to get rid of this 3 to the minus x, we multiply 3 to the x. Okay? So that's what we're going to do. So you have your 3 to the x minus 14 times 3 to the minus x equals 5. So what we're going to do is to multiply both sides of the equation by 3 to the x. That will make this term here disappear. Why? So let's do that. 3 to the x minus 14, 3 to the minus x. Then we multiply both sides of the equation by 3 to the x. Of course, on the other side, you will only have 5 times 3 to the x. So why will this work? If you multiply 3 to the x to this guy, you will have 3 to the minus x times 3 to the x. It will mean minus x plus x as an exponent of 3. And that's just 0. So basically, this guy here will cancel this guy here when you distribute this 3 to the x. Of course, 3 to the x times 3 to the x, that will give you 3 to the x squared. Minus, for this guy, as I have mentioned, 3 to the minus x will just cancel 3 to the x. So we'll be left with minus 14. And then, right-hand side, let's just write it as 5 times 3 to the x. And then we can move this to the other side of the equation. You will have 3 to the x quantity squared minus 5 times 3 to the x minus 14 equals 0. And then just like before, if you are not comfortable looking at this, you can do substitution. You let z be equal to 3 to the x. So you will get z squared minus 5z minus 14. This is equal to 0. So it's also a quadratic in form. I mean, this equation here is an equation quadratic in form because we were able to write it as a quadratic equation. Then you can find the value, or you can solve this using factoring, using quadratic equation, whatever you want. But let's try factoring here. You can factor this expression. Try to practice on that. This guy here, it's z minus 7 times z plus 2. So try to practice on factoring. You will get this. And therefore, z minus 7, this is equal to 0, or z plus 2 equals 0. Or here, you will have z equals 7, or z equals minus 2. We bring back z. Okay? We bring back 3 to the x. Z equals 3 to the x. So you will have 3 to the x equals 7, or for the other guy, you have 3 to the x equals minus 2. Okay? But take note of this. This cannot happen because an exponential expression, okay, will always be a positive number. This is not defined. So not possible. Okay? So this is only our chance. So just like the previous example, we can get the log base 3 of both sides of the equation. So log of 7 base 3. Okay? Let me clarify this. Okay, so that's fixed. And then again, this x will just go down. And then you have log 3 base 3. So x is equal to log of 7 base 3. So this is our final answer. This is the solution. If you want to test it, it's totally fine. But you will get the answer. Okay? So try to practice on the examples or exercises on pages 75 to 76. So you have a lot of equations there. So try to work on them to practice. Okay? And if you have any questions, don't hesitate to message me or to come in during the office hours. Okay? So that's it for my discussion, and thank you.